force in the rope. So if that's the case, we can do something cool here where I know that the acceleration is equal to the net force over the mass, right? I can solve for the acceleration directly because if I look at the force diagram, the force that's unbalanced is the tension. So her acceleration is 5.2 newtons, that's what it says in the problem, and the mass of the sled is 8.4. Okay, so 5.2 divided by 8.4. So the acceleration is about 0.62 newtons. Oh, not newtons, meters per second. So this sled is moving to the right and speeding up 0.62 meters per second for every second. What about the girl? Now, one thing you'll notice is the girl is so much more massive, so her acceleration is probably going to be less. So still, if you look at the diagram, the only force that's unbalanced is the tension. It's the rope force. And this girl's mass is 40. Okay, 5.2 divided by 40. 0.13. So it's funny that they both start from rest, so the sled is speeding up much more than the girl. So if we were to think about the halfway point, they're not going to meet at the halfway point. They're actually going to meet somewhere over here because this is going much faster. It's speeding up faster, which means that its overall speed is also going to be faster. So if we looked at any moment, it's going to be going faster, except for the beginning and stop. So how do we find out where? Okay. So once we have this idea here, what we're going to do is we're going to transition to understanding the kinematics. So let's do, we know that the sled, the position of the sled is equal to 1/2 the acceleration times time squared plus initial velocity times the time. That's for the sled. Now, we know the acceleration value. It's accelerating to the right, so 0.62 time squared. What's nice though is it started from rest, so that's a zero, that term is 0 there. So if I want to get the position of the sled, it's going to be equal to 0.31 t squared. Now, what about the girl? Right? The position of the girl is equal to 1/2 a t squared plus v0t plus, sorry, it's messy, plus, so we left a term off here, we left the plus 0 off here because we're going to assume that this started at 0. So where does the girl start? She starts all the way out here at the 15 meters. So 1/2, the acceleration is 0.13, but she's accelerating left, so negative 0.13 t squared plus, that term is 0 because it started from rest, so plus the 15. And I know the t's are the same, I know the x's are the same, and so you can either set the t's equal to each other and solve for x, or you can set the x equal to each other and solve for t and then plug back in. This might be interesting if we set the t's equal to each other. So if I look at this one, x over 0.31 is equal to t squared. If I plug that in here, I end up with x is equal to negative 0.065. I'm going to put in t squared, which is x over 0.31 plus 15. So x is equal to, oh, I just looked at it, 0.21. Negative 0.21x plus 15. I'm going to add this to both sides. This is already 1x, so this is 1.21 x is equal to 15. So x is equal to 15 divided by 1.21. So 12.4. Now that's a distance, that's going to be meters. Now the question is, how far from the position does the girl do they meet? So she is all the way out here at 15, and they meet at 12.4. So if this is 15 here, and they meet at 12.4, so it looks like she moved, what would that be, 2.6 meters. Thanks, that was hard. Let's do 39. So 39 says, a sphere of mass 3 times 10 to the negative 4 kilograms is suspended from a cord. A steady horizontal breeze pushes the sphere so that the cord makes a constant angle of 37 degrees with the vertical. Find the push magnitude and the tension in the cord. Okay, this is actually like legit easy. So here's the ceiling, whatever it's suspended from. Here's the cord, here's the sphere. Now the thing about this is it says it's like 3 times 10 to the negative 4 kilograms. It's a very small amount. So think like a ping pong ball. Could a ping pong ball get pushed by a breeze and swing out like this? It totally could. So, and it says 37 degrees. Now, for those of you who've been paying attention, why do we use 37 degrees? 37 or 36.9, because that gives us an indication it's probably going to be really close to a 3, 4, 5 triangle. So we have our picture. Let's draw the forces. There's the weight, mg. Now, it's here, and it's been blown here, and it's staying here, which means the acceleration is equal to 0. Therefore, the net force is also equal to 0. So the cable, the cord, whatever it is, pulls it up and to the right. And since it's pulling it up and to the right, we have to consider the fact it's pulling it to the right and up. Now, why did it swing at all is because we have some stiff wind pushing it this way. So this is the force from the breeze on the ball. And these forces balance. This up component balances the down. This right component balances the force from the breeze. And now I think we can do these things. So this is the tension in the cable here. Three times 10 to the negative 4. Okay, so it tells us the mass of the ball is equal to 3 times 10 to the negative 4 kilograms. No big deal. So let's think about this. We know the net force in the x direction is equal to 0. The net force in the x direction. Well, how do we express the net force in the x direction? Well, what do you want to call this thing here? This is t. Let's call this t in the x direction. So what are the two forces in the x direction? It's the tension in the x direction minus the force from the breeze on the ball. That says B on B. Well, if net force in the x direction is 0 and that's 0, that means that the T in the x direction is equal to the force of the breeze on the ball. Now, I don't know either of those though, so we can't do much there. Let's do the y direction. The net force in the y direction is equal to 0. The net force in the y direction, well, what's in the y direction? Let's call this Ty. That's the tension in the y direction. Feel good about that. So this is, I have Ty minus mg. And since these are both equal to each other and that's 0, I end up with T in the y direction is equal to mg. But I actually know these things. This is 3 times 10 to the negative 4, and this is 10. So T in the y direction is equal to 3 times 10 to the minus 3 newtons. So that's cool. So this one's 3 times 10 to the minus 3. I like that. Can I use that information and figure out the Tx? Well, how are Tx and Ty related? Well, what's nice about vectors is you can slide them, right? So what if I took this vector and I slid it up to here? Nothing has changed about my picture, except for now I know that this is 37 degrees, that's 37 degrees also. Now I know it's here, in this picture it's here, it says 37, but those two angles are alternate interior angles, I know they're the same. So this is Tx. How are Tx and Ty related? This one's the opposite, this one's the adjacent. Can I relate them through the tangent? So, tangent theta is equal to the opposite divided by the adjacent. So if I want to solve for Tx, this is 3 times 10 to the minus 3 times tangent 37. Zero point zero zero, 22 or 23? 23. This is also like 2.3 times 10 to the minus 3 newtons. Now, what I like about that is that now I have the Tx. So it tells me that the Tx is equal to the force of the breeze on the ball, which is 2.3 times 10 to the negative 3 newtons. That's how much force the breeze is putting on. So it all comes from the force diagram. And now if you want to get the actual tension in the cable, you can either use the Pythagorean theorem, or you could use the sine or cosine, it doesn't matter. So according to this diagram, the tension squared is equal to the Tx squared plus the Ty squared. Typo.